if it works.
Yes, it works. Yeah.
Mm-hmm.
First of all, what is low rank optimization? Low rank optimization is when our goal is to optimize. So we are trying to minimize a certain function that depends on the matrix. So typically, general optimization problem is the following problem, right? So we minimize or maximize some function, let's say f of w. So we are trying to minimize it. And we assume that W is taken from some set omega. So this is the general optimization problem. So when low rank optimization is when our omega, so low rank optimization is the following case. When omega is the set of all matrices, let's say it is the set of all matrices with dimensionality, let's say m times n, for which we have one assumption that the rank of matrix is not greater than some parameter k. So this is this problem when we are optimizing over this set is called low rank optimization problem. So why this problem is interesting? First, let me just give you some examples of low rank optimization problem. So the classical example is so-called low rank approximation. So suppose that examples of such problems. So example number one, when our function is a function of matrix, which, so roughly speaking, our function is a function of matrix, so that we try to minimize, which is equal to, roughly speaking, some distance between matrix M and fixed matrix, let's say A. Say A is given, so A is some given matrix. So it's given to you, it's part of the input. And we can measure the distance from matrix M and matrix A. So typically we can measure it in terms of Frobenius norm. I just reminded that what is the Frobenius norm of matrix? So when you are given some matrix Aij, then Frobenius norm of that matrix is actually the sum of squares of entries under the root. So this thing is called Frobenius norm of matrix. So a typical example is of low rank optimization problem. By the way, let me now introduce maybe some notation. So let's this set, let maybe denote it somehow. I don't know, S N M K, right? So this is M and K. M and K. So this is M times N matrices with rank less or equal than K. So by the way, if we are considering this this example, when we minimize, roughly speaking, this function, maybe someone remembers what is the solution. So when Frobenius norm is minimized, and we minimize over all matrices with of rank not greater than K. So what is the solution of that problem? Maybe someone is familiar with that.
Singular value decomposition? No?
Yes, of course, this is famous singular value decomposition. So how to solve that problem? It's easy that we have to find so-called singular value decomposition of matrix A. So it's typically like sigma 1, U1, V1 transposed, sigma rank of A. Okay, maybe let me just here just denote it as R. Sigma R, UR, VR transposed. So we first represent matrix in terms of singular value decomposition. And it turns out that the argument, so the solution to that problem, roughly speaking, is M star, which is equal to this. Of course, singular values are ordered by value, so they're always non-increasingly ordered. So roughly speaking, when you take only the first k terms in that sum, so roughly speaking, when you take this sum, sigma I ui vi transposed, when I is from 1 until k, so only the first k term, this is so-called truncated SVD. So there is such thing as singular value decomposition, and when you order all the terms in singular value decomposition and take only the first k terms, so-called truncated singular value decomposition, this exactly gives you the solution of that problem. So this is classical result, which is called Eckert-Jung-Minsky theorem. Eckert-Jung-Mirsky theorem. So it turns out that when you want to approximate some given matrix A in terms of Frobenius norm, then the best way to approximate is to find with some matrix whose rank is bounded by some k, right? Whose rank is not greater. Then the solution to that problem is just singular value decomposition of the matrix A truncated at kth term. And this is what Eckert-Jung-Mirsky theorem tells us. Actually, Eckert-Jung-Mirsky theorem tells us even more. Actually, you can here use not necessarily Frobenius norm, but so-called any unitarily invariant norm on the set of matrices. But we are not going to, of course. So, you see that low rank optimization, it first appeared as a problem of approximation some matrix using another matrix whose rank is bounded. Then this leads us to an idea of SVD, where the SVD, there we have principal component analysis, right? So roughly speaking, Eckert-Jung-Minsky showed the connection between low rank optimization for a specific objective and principal component analysis. Actually, what principal component analysis does, you know that principal component analysis is just, again, part of data science where we take some data matrix, right? Then our goal is to find approximation of that data matrix with another matrix whose rank is not greater than k. This whole area is called principal component analysis. So it turns out that standard principal component analysis is just special case of this low rank optimization problem. Okay, now maybe, but this is not the only case of low rank optimization problem. Another case is so-called robust PCA. Actually, it's called not robust, sparse PCA. So the first, roughly speaking, the classical PCA, you know that it was invented by the great English mathematician Pearson, right? It was in something like that, right? And then in the 70s, this showed that, roughly speaking, PCA is the same thing as singular value decomposition. And this is, roughly speaking, low rank optimization. This is a subset of actually, this is subset of low rank optimization. So this can be understood as low rank optimization. And this was understood in the 30s, roughly speaking. This was made by Eckert-Jung-Mirsky. Then what happened? Approximately in the 80s, 90s, there appeared so-called robust, different robust versions of PCA. Yeah, I think they're called robust PCA. So robust PCA means the following thing. Principal component analysis. Then when we are given some matrix and we are trying to approximate that matrix, but using slightly different norm. So we are trying to, roughly speaking, to minimize M minus A, but here we use so-called L1 norm. So we are trying to minimize over M when M is a M times N matrix with rank not greater than K. Where, what is, roughly speaking, the norm of the matrix in terms of L1? It is just simply the sum of all elements. So roughly speaking, the sum of all elements, all absolute values of all elements. And what people learned when we are making very little change, right? Instead of Frobenius norm or any unitarily invariant norm, when we put L1 norm, then everything becomes more complicated. It turns out that this problem doesn't have good algorithm. Roughly speaking, this problem is so-called, there is such thing as NP-hard problem. So roughly speaking, this problem cannot be solved efficiently. Only one thing is changed. You use instead of Frobenius norm. So I remind you that in the Frobenius norm, so roughly speaking, the square of Frobenius norm is just the sum of Aij squared, right? So this is Frobenius. You just square all the entries of the matrix. So if you, instead of squaring, you just take absolute values, then everything becomes more complicated. You do not know how to solve that problem. There are many different approaches how to solve that problem, but none of these approaches actually provably guarantees you that the solution can be found efficiently. So this means that any algorithm will, for any algorithm, there are some worst case examples that will take a lot of time. So that's what means that the problem is NP-hard. But robust PCA, what is the meaning of robust? Robust PCA is just the same thing as principal component analysis. But robust, why it's called robust? It's in statistics, there is a very fundamental notion of robustness. This means that, roughly speaking, the hyperplane that is hyperspace that is spanned by principal components in standard classical principal component analysis, it's very, let's say, different so-called outliers in the data can substantially change the solution. So if you apply PCA to data which is not, let's say, which contains some outliers, then PCA will fail to work. This is well-known fact that data containing outliers demonstrate very bad behavior when you are trying to find the principal components in such data. So therefore, you should instead of classical PCA, you should use robust PCA. By the way, robust PCA, it's a story of 80s and 90s. The guy who introduced this, Emmanuel Candes, a famous modern statistician. So now, what else? What then? Maybe you heard about such thing as Netflix price. Who knows what is Netflix price? This was in the already recently. There was a price which was announced by the company named Netflix. Maybe someone heard about that?
Yes, it's they like provide some problems, yes, for data scientists, and they should submit their work.
Well,
Something
yeah,
like
Like you can cancel anything.
company whose business model is the following. They just this is a company. They deliver like you can watch different movies, right? Using this channel, Netflix. There is a channel also, but besides channel, they also sell, I think, compact discs and many. So this is roughly speaking. The business model is to sell different movies, produced movies, right? And not only movies, series. So any different entertainment production is sold by using Netflix. And what they have the following situation. They already had a large number of customers and large number of different units that they sell. So roughly speaking, so they have like customer 1, customer 2, customer 3, etc. And they have like movie number 1, movie number 2, series number 3, I don't know, etc. Different units that they sell. And what they know, for example, they have some story. So for example, the customer number 1 watched this movie and graded it like 8 on IMDb. Then he looked to that thing and graded like, this was graded like 2. Something not graded at all, because a lot of things are not seen. Some movies are not seen by these customers. So there we can write down asterisk, right? It means that nobody, this customer number 1, 2, the second customer maybe not seeing at all anything. So, absolutely.
So is it a problem of recommendation or?
Yes, it's called, yeah, of course, this is a problem of recommendation. And third customer, maybe, again, he watched this movie, graded it like 1, and then, and etc. So we have a large matrix, so-called customers, and I don't remember how they call, let's say customers goods, right? So they have matrix, customers times goods. And of course, the goal of this company is to make more money, obviously, and to sell some products to users who haven't yet seen some product, for example. For example, some new movie, I don't know. So this company should kind of advertise to you something that you will probably see, roughly speaking. So that's why it's not like randomly to advertise something which is popular right now. For example, now new movie comes, right? For I don't know, Suicide Squad, and we can stupidly advertise Suicide Squad to all of you, right? Or vice versa, we can look to your previous history, what you liked, right? And to advertise something that you probably will see. For example, if we know that you are some kind of, you are interested in history, and we see from the from what you already see that you like historical, I don't know, movies, right? That dedicated to some Victorian era, right, in the history of England. So we were going to offer you some movies with that topic. So how to solve that problem? Netflix published their database. So they published, of course, not the, I don't think that is the whole what they have, but they, roughly speaking, made some extraction of what they have. So of course, everything was anonymized. Customers are anonymized. Even units probably are anonymized. These goods are, so then they have this large matrix. What kind of matrix is that? Some entries are not defined. Moreover, it's a sparse matrix. 99%, let's say 99% of entries are just empty for very simple reason. For example, on the market, we have 1,000 movies that are sold right now, right, on the market. And every customer only saw, for example, 20 movies on, or even if he saw, maybe he didn't graded them. So actually, general typical customer maybe graded 20 movies from this 1,000. So most of the entries will be just zeros, not zeros, but asterisks, not defined. So what was then the problem? The problem was just to so-called make completion of the matrix. So roughly speaking, you have to here what is not given. You have to put here something. So this is called matrix completion problem. Matrix completion. So your goal is, roughly speaking, to put something into those cells which contains asterisk. And how to put it? There are many approaches, and it turns out that very successful approach is the following one. Just to solve the following problem, you have to find matrix of low rank, lowest rank possible, so which will approximate this given matrix at which end in those terms that are given to you. So understood? So you have some matrix which is okay, maybe not M, let's denote it as A, right? So you are given this matrix which is partially defined. So what does it mean? It means that it is allowed that some of the entries are just equal to 0, right? So roughly speaking, you can introduce a new matrix which is naturally can be called like I don't know. So let's now introduce a new matrix which is called mask. Let's say this is mask. This is this new matrix whose entries Mij is defined in the following way. Mij is equal to, let's say, 1 if Aij is not equal to asterisk, and 0 otherwise. Something like that. So understood. So this is just indicator matrix that is equal to 1 only when this matrix is defined, when corresponding entry is defined. And then what kind of function we can minimize? We can minimize the following function. So we have the function f of m, which is equal to, so you have to sum over all entries Ij. Oh, actually, we don't need mask matrix. Sorry, forget about mask. I will just make it simpler. So all entries for which Aij is defined, we are going to Aij minus Mij squared. So roughly speaking, M is a matrix Mij, right? And we just define the following function. So the M is roughly speaking the distance until A, but only that concerns only those entries that are given to you. Understood? So we are trying to measure. So this is also some kind of distance between A and M, but this distance is very strange. This is very similar to the Frobenius distance, right? But the difference is that instead of Frobenius distance, we sum over all possible entries, right? Over all possible Ij indices. But here we sum over only those Ij that are given. So for which Aij is defined. So for which the matrix A is given, the entry of the matrix A is given. And then our goal is to minimize this expression. Of course, we assume that M is a matrix of rank not greater than K. So this famous problem is called matrix completion problem. Completion problem. And it turns out that this is one of the most, best way to solve the recommender. So this is the problem of Netflix. So this is called recommendation system. So when, roughly speaking, you have this matrix of preferences of user goods preferences, and you approximate the whole this matrix with matrix whose rank is kind of bounded. So for example, it's not greater than, I don't know, 100. So you see that typical metrics of this kind, the number of customers could be like billion easily. For example, for Netflix has customers all over the globe, right? So maybe billion people are in their database. Times the number of different movies, so it's like 10 to the 4, something like that. The total number of different movies, different entertainment goods, series, everything. There are plenty. I think that this at the scale of 10 to the 4, 10 to the 5. So you have this large matrix, whose entries is not defined everywhere. It's a sparse matrix, and you have to approximate that matrix with another matrix whose rank is not greater than something, not greater than maybe 100. And it turns out that this is one of the best ways to solve the problem of recommendation. And general problem now appears. So there are many different approaches to that problem. How to solve that problem? This problem, by the way, matrix completion problem, is also in NP-hard. So there are no any good algorithms, probably good algorithms for that problem. Even that problem cannot be solved in general by ideal algorithm that works for any input matrix. And then we come to the general formulation of low rank optimization task. In low rank optimization, our goal is to minimize some function over this. So the general problem is like that. Minimize f of m when m is a matrix, m times n matrix, whose rank is not greater than k. So then, how it is naturally to solve that problem? So you see here we have uncomfortable search space. So the set of matrices whose rank is not greater than k, how to handle with that strange even if what we learned, by the way, even if this f of m is convex, this still doesn't mean that this problem is easy. You know that the convex optimization problem are tractable. This is well-known fact that when you just have convex function, then the minimization of that convex function is tractable when, roughly speaking, there are no constraints. Unconstrained convex optimization is tractable. Or if the domain over which we optimize is convex itself. If this thing is convex body, this is a convex function, then the minimization of convex function on a convex set is tractable problem. This can be solved. But minimization of convex function over this set is intractable in general. It's NP-hard problem because this set is highly non-convex. If you will draw this set of matrices with, roughly speaking, whose rank is not greater than k, if you will draw this set is, I don't know, it looks like that. Maybe I don't know. So it's just is a union of. So when, roughly speaking, you know what is the. So it's highly non-convex. It's, if you will draw it, it's not possible to draw it even in low dimensions. But maybe in low dimensions it will be the best way to visualize this set. This is just intersection of different rays. This is highly non-convex situation. Since this is non-convex set, then we cannot apply all the mathematics that was developed for convex optimization. But still, people try to solve that problem using convex optimization. How they solve this by convex optimization? They do the following simple trick. So this set of matrices whose rank is not greater than k can be, we know a very simple fact that if we have the matrix whose rank, so suppose that this is M times N matrix, right? And we know that its rank is not greater than k. Then what we know about that matrix? We can, of course, find singular value decomposition, right? So therefore, this matrix can be represented like sigma 1, u1, v1 transposed, sigma k, uk, vk transposed. And it's easy to see that this is the same thing as the following expression. So you can just here put u1, uk, roughly speaking, left singular vectors. You can put it, and this will be matrix equal to, let's denote it as u. Then times diagonal matrix with entries equal to sigma k. And here we will put matrix v1 transposed, etc., vk transposed. So roughly speaking, what does it mean? It is simply means that our matrix M was represented as U times sigma times V transpose, right? And it's easy to see that sigma is a matrix, roughly speaking, for which we can, for every entry, we can calculate the square root. So therefore, you can here represent it as sigma to the power of 1 over 2, sigma to the power of 1 over 2, V transpose. So roughly speaking, any matrix whose rank is not greater than k can be represented as a product of two matrices, x and y. So, and what we know about x, by the way, here, okay, k prime is less or equal than k. Right? So what we learned that, and what about the dimensionality of x? It will be m times k prime, and y will have dimensionality. What kind of? It will be, it have k prime times n, right? So there is a simple basic fact which we can learn from linear algebra. From linear algebra, we know that actually the set of matrices whose rank is not greater than k, it is just equal to the set of matrices that can be represented as x times y, where x is m times k and y is k times n. So this is basic interesting phenomenon, that any matrix of rank k can be just decomposed x, y, where x is m times k, y is k times n. So what first people offered for a problem of low rank optimization. So since our problem was initially this problem, right? So why not to solve another problem, f of x times y, to minimize this function, but x will be then just unconstrained, no constraints, will be m times k, and y will be k times n. So understood. So we are making, so we are instead of maximizing f of m, we will maximize f of x times y, where x and y are some unknown matrices. What happens in that case? Unfortunately, by the way, let me ask you, because I don't ask any, who can tell me what is the problem with this? So if we are going to optimize, instead of optimizing the function of the matrix M, whose rank is not greater than k, we are optimizing the function of the products of two matrices. But now x and y are unconstrained. This is what matters, because before that we had this assumption that M is satisfies some constraint, but here we don't have any constraints, but still there will be some problem. What do you think? What is the problem? what kind of problem we still have? So before that, we had convex function, right? F of m, but the constraints made everything complicated. Here, we reduced the problem to another problem for which there are no constraints. X and Y are unconstrained matrices. There are no any constraints. But what is that? What do you think?
So not equivalent to each other, these two problems.
Problems are absolutely equivalent. If you solve the second one, then you will solve this first. It's easier how if you solve the second problem, you just then define m equal to x times y. And this gives you the solution of the first problem. And vice versa, by the way. If you solve the first one, you will solve the second one. So these two are absolutely equivalent.
Is it no longer convex?
Correctly. The function f of x times y is no longer convex. You lose the property of convexity. But the function of f of x times y will have another property. It is convex on each variable x and y by itself, but not jointly convex. So roughly speaking, we have the following situation. We have the situation when, so if we have fixed x, so suppose that x is fixed. So let's even somehow denote that the f, xf, fixed. Then this problem can be efficiently solved. So you can minimize over y efficiently. Why is that? Because this will be, roughly speaking, what? This will be convex. Why? Because x is, you can treat xf as constant, right? So then this thing depends in a convex way on y. Because roughly speaking, this is what? This is linear function. So here we have linear function. And to that, we apply convex function. We know that if convex function is applied to linear function, the result is always convex, right? So therefore, this function overall going to be convex. And even more, vice versa, if you have fixed y, then the same is true. You can minimize this thing, right? Over x. And again, you can solve why, because this function is convex. This is linear over convex over linear. So these two problems can be solved efficiently because these two problems are convex optimization problems. Roughly speaking, what is good about convex optimization? The convex function is function like that, right? And any local minimum is a global one. So any algorithm, for example, any gradient descent algorithm will solve the convex optimization problem. You just have to, roughly speaking, minimize, go in the direction of opposite to the gradient. Gradient shows you the direction in which your function increases. Opposite to the gradient shows you the direction in which your function decreases most rapidly. So you can move always in the direction of opposite gradient, and you finally will achieve local minimum, right? And this local will be just global. This is nice property of convex functions. Unfortunately, this is not true for non-convex. You know that non-convex functions could be something like that. So for non-convex, so this idea brought us to the idea of so-called alternating algorithm. Alternating algorithm is simple thing. What we are doing in alternating algorithm, we are just for, let's say, t equals to 1 until capital T. So first of all, you denote x0, y0, and somehow initialize them. And then the whole idea of alternating is simple. At step number t, you define xt. So first you minimize over t. So you calculate the minimum of that function x, y, t minus 1, right? Over all x's. And then the argument at which this minimum is attained is xt. Then when you, after you calculate xt, then the next step you calculate yt. So this is an argument at which the minimum is attained of that function f of xt y. And this, you repeat this thing until it converges. Roughly speaking, you repeat this many times. So roughly speaking, you start from x0, y0, initialize them randomly. Then for fixed x0, you optimize over x and you find x1. Then for fixed x1, you optimize over y, you find y1. And then at the next step, so given xt minus 1, yt minus 1. Sorry, here, yeah. Given xt minus 1, yt minus 1, what you do? You first optimize over x, second is yt minus 1, right? Then you find xt. And then for given xt, you optimize over y, and you find yt. So this basic algorithm is called alternating algorithm.
So it is an iterative method.
Yes, of course, this is an iterative method when you, roughly speaking, calculate iteratively. Roughly speaking, what you do, this is the most stupid way to optimize a function of two. This is, by the way, not, this is just general idea from optimization. When you have a function of two variables, right? And suppose that your function is convex on x, convex on y, but not jointly convex. Very easily can happen. This situation can very easily happen when you have convexity on one variable, convexity on another variable, but together they are not convex. This is our situation. But if you have this situation, what you can do? You can alternatingly optimize it. So you first optimize over x, achieve the minimum over x, then you optimize over y, achieve minimum over y, and then again over x, and then unfortunately, this algorithm can converge to something not very good. So this is the basic problem of optimization. When your function is convex, this is a nice situation. But in reality, you can see this kind of functions. You see? So there are one global minimum of that function, right? And there are suboptimal minimums. So this one local minimum, this one local minimum, this very bad situation when you have these local minimums that are kind of oscillatory. So you can randomly fall into some random point. This is what people from optimization most afraid of. When you have this kind of landscape, when you can fall into random point, just when you just when the algorithm converges to something and you cannot do anything with that. So this is classical way to solve the problem, and this way, by the way, is sometimes leads to suboptimal solutions. So it's easily that you can fall into some random local minimum like that. It's not necessarily, this algorithm not necessarily converges, and even more, this algorithm doesn't have any theoretical guarantees. You will not find any. So everybody uses that algorithm. This is quite famous algorithm, but nobody has any theoretical analysis of that algorithm because theoretical analysis is quite hard. We can only say that there are only very few cases when this algorithm is successful. For example, one of the cases is when your function is, let's say, f of m. Suppose that your function is, let's say, has the following structure. It's like a times, so b minus a times m. And this is Frobenius norm, for example. So when you have this kind of, and when you put here f of xy, you will obtain b minus a xy. So for this interesting case, it was proven that this cannot happen. This situation cannot happen. Only one global minimum exists. So only one, so local minimum. So this function is not convex, still not convex. But the energy landscape of that function is quite nice. Why? Because any local minimum, so roughly speaking, all critical points of that function are either global minimum or saddle point. There are no local minima. So what does it mean graphically? Graphically, this means the following situation: when you have energy landscape of this kind, seconds. So roughly speaking, you have one local minimum, one global minimum, and this is local minimum, and many points critical. So this is critical point, this is critical point, and all critical points are saddle points. So all of them are saddle, and there is only one global. And this is actually, of course, the only local minimum. So this is a nice situation, and this is true for this function. B minus A Frobenius, right? But only for this. In general, unfortunately, this is not a nice situation. So for this alternating algorithm works. What I'm trying to present, my approach is another one. So I developed my own algorithm, and this is maybe my goal of today is just to present this algorithm. The idea is simple. So let's now, it's well-known fact. So well-known fact from optimization that suppose that you are trying to solve the problem, you are minimizing some function, right? On the condition that another function is equal to 0. So suppose that g is non-negative, always non-negative, but you want to minimize a certain function given that g of m is equal to 0. So the famous fact from optimization that this problem is equivalent to the following problem: f of m plus lambda g of m. So you minimize this function without any constraints, but lambda is positive, and roughly speaking, lambda is large. So roughly speaking, this means the following thing: that any constrained optimization problem can be turned into unconstrained optimization problem, but you have to add here this function, which is called penalty function. This is called the method of penalties. Any textbook in optimization, it includes some chapter which demonstrates that these two problems are, roughly speaking, so this problem is not equivalent to one single, but for a collection. So roughly speaking, if you are able to solve this problem for lambda equal to lambda 1, lambda 2, lambda 3, etc., so that lambda I goes to plus infinity. So roughly speaking, if you are able to add any penalty for arbitrarily large lambda, you will eventually, so you can choose lambda, always you can choose it such large that this problem will always give you the solution of this problem. So for large alpha, this problem gives you the solution. So if lambda is large, the solution of the second problem will give you the solution of the first problem. So now the question is, if we have here low rank optimization, so our goal is to, so we have to choose a function so that this function is equal to 0 if and only if our matrix belongs to that class. How to choose such function? There is a natural function of this kind. This is called Caifan K antinorm. So Caifan K antinorm is the following function. So suppose that m is a function with certain singular values, so with a certain singular value decomposition, roughly speaking, sigma 1, u1, v1 transposed, sigma s, us transposed, right? Suppose that you have, so the idea is the so-called Kaifan D antinorm is the following thing. This is called Kaifan D. You are, roughly speaking, you are summing all singular values starting from D plus 1. So actually, we can consider, of course, the squared variant. Okay, if let me ask you the question. So let's suppose that we defined the function in the following way. So this is so roughly speaking, this is just the sum of singular values starting from D plus 1. Then when this thing is equal to 0, who can tell me? What does it mean that this function for some matrix is equal to 0?
All singular values starting from D plus 1 are 0, or sum up to 0.
Not just sum up, but they should be equal to 0 because this is the sum of squares, right?
Yeah.
And what does this mean?
Which component should be clear?
That the rank can be dropped to D.
That the rank is not greater than D, exactly. So roughly speaking, this equal to 0 if and only if the rank of M not greater than D. So roughly speaking, if all singular values starting from D plus 1 are equal to 0, then only D singular values survive in singular value decomposition. And this means that the rank is, so roughly speaking, if you choose G of M as roughly this Kaifan D antinorm, not D, but K antinorm squared, right? Then it's easy to see that this problem will be just exactly equivalent to minimization over the matrices of rank not greater than K. And then we know that this is equivalent to this problem. So therefore, what we learned, in order to solve low rank optimization problems, we need to be able to solve the following kind of problems. We need 4 minutes left. Let me just, last 4 minutes, I will just finalize and give you the description of the algorithm. So it turns out that low rank optimization is equivalent. So minimization of function M over matrices M times N of rank not greater than K. It is the same thing as minimizing f of M plus lambda K antinorm for a lambda large, right? And then after we introduce this, we recall what is actually the K antinorm. It is the sum of all starting from K, all singular values, right? So let's here introduce maybe in the square means that this the singular value of the matrix M, of course. So this is the rank of M. So squared, right? And there is a well-known fact that what is this? This is nothing else as M minus SVD of matrix M, which is truncated at case. So roughly speaking, this is nothing else that the minimum of M minus S, not S, maybe introduce it, maybe let's use M minus X squared, when X is taken from M and K. So roughly speaking, we know that this fact we know from Eckert-Jung-Mirsky theorem that the minimization of M minus X Frobenius norm squared over X with rank not greater than k is exactly attained, the minimum is attained on the SVD. So roughly speaking, here x is the same thing as SVD of m truncated at k's term, right? And it's easy to see that this difference will have Frobenius norm exactly equal to this expression. So therefore, what we came to? We came to the following problem, that our goal is to minimize the following. So here you have minimum over x, right? And this thing you have to minimize now over m. Then now afterwards we can put here minimum over there, and we come to this problem, that we have the following function that depends on two values, f of m and x. So this is not f of m, maybe let's denote it as g, not g, let's denote it as k, no, not k, f g h, h of mx, which is equal to f of m plus lambda m minus x Frobenius norm. And now this function h of m x should be minimized over two parameters. First, unconstrained parameter m, right? So this is just no constraints. This is m times n matrix, right? And the second parameter is x, which is constrained. But what is nice? The nice thing is that for fixed m, minimization over x can be easily done. Because roughly speaking, when m is fixed, when we minimize this, so when m is fixed, the minimization of this thing over x, it's easy to see that this argument at which this minimum is attained is exactly equal to, roughly speaking, the SVD of m truncated at k's term, right? So the minimization over x for given m, when m is fixed, can be done easily. Moreover, for fixed x, the same thing, minimization of h of m for fixed x also, so this is unconstrained convex optimization. So this is, roughly speaking, convex optimization problem. So this thing also can, so again, we can apply alternating algorithm, because the minimization over both parameters can be done very fast. You can minimize over m, then over x, then over m, and vice versa. You can alternatingly do that minimization. And this gives us new algorithm for low rank optimization problem. So this is, roughly speaking, the basic ideology around this problematics of low rank optimization. Do you have any questions? Let's finalize on that.
You mentioned, oh, sorry.
What?
I wanted to ask, so everything you explained so far, you explained it in terms of minimization problem. And I wonder if, what if we have a maximization problem? So would there be any difference, or it applies only to minimization problems?
This is, of course, applies to minimization. For maximization problem, the situation is quite different. Even if function is convex, the maximization of convex function, it is the same thing as minimization of concave function. And this is believed to be true even without constraints. So roughly speaking, to maximize convex function, even if you don't have any constraints, it is a hard problem. This is absolutely another problem. So maximization, when you apply it even to convex function, is hard. But here we are dealing with the following case. The minimization of convex function can be done efficiently, right? But the problem here was that minimization, we are minimizing the convex function, but over a matrix whose rank is bounded. So slightly, yeah, it's not easy to just apply something which you developed for minimization. It's never easy to apply for maximization because they're absolutely different problems. It's this typical situation in mathematics and optimization, that something which can be minimized quite efficiently cannot be maximized efficiently. Convex function, okay. Typical situation. For example, quadratic convex function. if you have quadratic convex function, then minimization is very easy task. But maximization of quadratic convex function is an NP-hard task.
I have 3 questions, actually 2 questions only. First, have you tried to apply this to some sort of problems? And second is, what do you mean when you say lambda is large? What is large in there?
Yes, of course, this was applied to some problems already, but let's say this was applied to f of m was not even convex. So actually, currently I'm in the project where I develop new methods for manifold learning. And this is the algorithm that is the key algorithm in that. But there, it's in the problem that we solved there, it's even more complicated because there you have many terms of this kind. So you have kind of like, it could be 100 terms of this kind. So, but this is, but also the alternating scheme. By the way, this algorithm that I call it alternating scheme. Unlike the previous is alternating algorithm, this is classical one. And this one, I call it alternating scheme. This was applied, and actually this works. This thing works. So we find efficiently the optimum. And concerning large lambda, this is of course one of the parameters of algorithm. So you here, how it's called, the method of trials. Just extract some value lambda equal to 10, and this gives good result. But what is interesting that this is one of the experimental facts that we observed, that when you increase lambda and you make it too large, then algorithm unfortunately converges to some bad local mean. So when you put lambda equal to 100, I don't know, for 100, maybe if you put like 1000, very easily you can, this algorithm can fall into some local minimum, bad local minimum. So this is the problem of that algorithm for large lambda. So now currently we are working on how to solve that problem. So unfortunately, you cannot guarantee. So for large lambda, that alternating scheme will converge. Also, there is a paper of mine where I apply that algorithm, but to infinite dimensional case. So there, my function is, so roughly speaking, there's infinite dimensional matrix. This matrix is infinite dimensional. All matrices are infinite dimensional, but still this can be done efficiently for certain reasons. So even infinite dimensional optimization can be done efficiently because, well, there is a good representation of those infinite dimensional objects and it converges somehow. So, and infinite dimensional case was quite successful. Infinite dimensional case, what was the reason why I started to do that in finite dimensional case? Because first, I applied this algorithm for infinite dimensional case. And when I saw that this works, then I started to apply it to a finite dimensional case. And now there is an interesting mathematics behind that algorithm. Roughly speaking, well, this is not what I plan to talk about today, but when you calculate this, according to alternating scheme, when you calculate for fixed x, you calculate over m, and then vice versa. For fixed m, you calculate over x. This corresponds to some process, like from xn you get xn plus 1, then you get xn plus 2, etc. Right? So this will be a chain of matrices, and it's easy to see that this operator, roughly speaking, so you have xn plus 1 equal to r applied to xn. So roughly speaking, xn plus 1 equal to r of xn. Okay, wait. So this is like xn plus 1. So xn plus 1 equal to r of xn. So this operator, so this, roughly speaking, the all local minimums to which you convert are, roughly speaking, fixed points of that operator. And this, it turns out that studying this alternating scheme, it requires understanding the fixed points of certain operator. fixed points are such function, such value for which, roughly speaking, x is equal to r of x. So x is equal to r. So that's why we have to study fixed point of a certain operator in order to understand the behavior of alternating scheme. So the general situation is like that. This thing works practically, at least for moderate lambda. And why it fails for large lambda, this should be understood. There are some theoretical explanations of that phenomenon. I already have it. But this is the beginning of the process, let's say.
You also mentioned that alternating methods may not converge. Are there any other methods that guarantee that convergence?
In general, there are no methods that with guarantees, with theoretical guarantees that will solve that problem. I mean, the problem of minimization of convex function over matrices of bounded rank, it's general NP-hard problem. There is such thing as NP-hardness, phenomenon of NP-hardness in optimization, not in only in optimization, in general in computer science, the problem of NP-hardness. One can prove that some problem is NP-hard. What does it mean? It means that there exists some classical NP-hard problem, like, for example, satisfiability, that can be reduced to that problem. And everyone believes that satisfiability doesn't have good algorithms, polynomial algorithms. There's a famous hypothesis in computer science, in theoretical computer, that P is not equal to NP. This simply means that certain problem like satisfiability doesn't have good algorithms. So the best algorithms will still be exponential or super polynomial or something like that. So there are no polynomial algorithms for this problem. There are no easy way to solve those problems. So then there are so-called NP-hard problems. These are problems to which satisfiability can be reduced efficiently. And these NP-hard problems, when someone says that the problem is NP-hard, means that if someone will find an algorithm that provably efficient for that problem, then it will be just a revolution in the modern science. So if someone will find an algorithm for low rank optimization problem that is polynomial, for example. So for example, for matrix completion problem, or for general minimization of convex function over this S of M and K. If someone will find an efficient algorithm, efficient means polynomial algorithm, means that the complexity of that algorithm depends polynomially on the size of the input. Then this will be a revolution. So that's why nobody believes that such algorithms exist. Actually, this is hypothesis that nobody knows how to prove that hypothesis, but everyone believes that this is true. P is not equal to NP means that there are no good algorithms. So which means that this problem that I'm trying to explain, introduce different algorithms, that's why these different approaches concur with each other, because nobody has good algorithm. So this problem cannot be solved in general. That's why everyone presents his own algorithm, and sometimes this algorithm is better, sometimes this algorithm is better, but there are no universally good algorithm for that problem. It means that this problem is NP-hard, roughly speaking. It can be theoretically proven that some certain algorithm solve this problem for all inputs with good complexity, like polynomial.
Okay, thank you.
Can I ask a question?
Yes, of course.
Like, so can we conclude that Kaifan key antinorm will be the same as penalty problem, like when JM is equal to 0, and it can be like covered as a subset of classical PCA or not? Because we have used Frobenius here.
Classical PCA, so what I just, actually this, I didn't today talk about that, but classical PCA means what? Means minimization of Frobenius distance, right? And this, well, actually, I'm able to prove the following fact. So, so this classical PCA is equivalent to minimization of A minus M, right? Frobenius. When M is not greater than of rank K, right? So this is a classical PCA problem. And if we apply alternating scheme, then this will become equivalent to, no, not equivalent. Yes, actually it is equivalent to this problem. M minus X when you minimize over unconstrained M, and X is M and K. So roughly speaking, of course, nobody is going to apply this alternating scheme to the PCA. Why? Because PCA has nice algorithm. PCA is one of those cases that can be solved efficiently. PCA, roughly speaking, when you minimize this Frobenius distance, this is a very nice case. The only well-known nice case, roughly speaking. For this case, everything can be made efficiently just by singular value decomposition, right? Nobody going to apply this alternating scheme for that simple case. But if you just do it and apply, then this problem, to that problem, you can apply alternating scheme, and there are many local minimas to which you can converge. And roughly speaking, the minimum that corresponds to the solution of the classical always will be one of those local minima. So roughly speaking, this SVD truncated at K's term will be always among the solutions of this problem. And even more, one can prove that this is the solution that always kind of for any lambda it is present. And even more, roughly speaking, you can always converge that solution with high probability. You can just randomly start from random initialization. With high probability, you will converge to that. So, of course, alternating scheme solves this standard problem. PCA can be also solved by alternating scheme, but nobody going to solve problem which we know how to solve. Alternating scheme was developed for problems that we don't know how to solve. But for this one, nobody is going to apply alternating scheme because there is a nice algorithm for PCA. This is singular value decomposition. And there are 10 different algorithms for finding singular value decomposition efficiently.
So open questions will be only for robust PCA and p-hards.
Yeah, for robust, for matrix completion, and not only for them. Actually, for example, when I apply this alternative scheme in my applications, f of m is not even convex actually. So for me, it's not a big, since okay, of course we are making theory for simple case. When you publish paper, you always analyze the case which can be analyzed mathematically. Mathematically, we can analyze the simplest case only when f of m is convex, etc. But in reality, this is the typical situation in optimization science. You are able to analyze something only for the simple case, but you are not going to apply it only for it. In practice, you are going to apply this algorithm for very complicated case. For example, when f of m is not even convex, f of m could be very complicated function, like for example, loss function of autoencoder. It is very complicated functions which is not even convex. And still, we can apply, in that case, we can also apply this alternating scheme. Hope that it will give us the solution.
Could you point us to the paper when we can read more about the method?
Right now, only one paper, which is, you can find, this is infinite dimensional case of that. I haven't yet published, so closer to the end of this year, I'm going to publish. So right now, it's only infinite dimensional case was published. I'm not sure that this is good paper to start the reading, because this is a paper which involves a lot of functional analysis. It's done in terms of generalized functions, temper distribution. You can Google it easily. Just my family name and generalized functions, and you will find the paper. But this is not the best, because there is quite sophisticated infinite dimensional case, and to start thinking about that one, it's better to start from finite dimensional case, of course, because already there all the interesting questions.
Excuse me. I missed the part where you were saying that we can decompose M as the product of two matrices X and Y. What was the problem with minimizing this? Like, why do we have to do it like separately?
Because this function f of xy is not convex. This is the problem. So roughly speaking, even if the function f of m is convex, this still doesn't guarantee that. So roughly speaking, f of m is convex, right? For example, like something like that, like a minus b m, right? Frobenius. This is convex function. It depends on m component. But when you put here as arguments this product of two matrices, this is going to behave in a convex way on x, in a convex way on y, but together it's not a convex function. So what does it mean? This, if you treat this function as a function of two variables of x and y, this is not convex function.
Okay. And also I have another question. When we were talking about Netflix price, you said that we can use M as a masked matrix, but then you said that there is another matrix that works better. And which one is it?
I just first I wanted to define that problem using masked matrix, but then I just saw that masked matrix is not needed at all. I can do everything without masked matrix. So this just was just a little, let's see, methodological error. Typically, masked matrix means the matrix that should kind of point to us to those entries that are defined. But okay, you don't need masked matrix. Was everything there was defined absolutely correctly without any masked matrix. So roughly speaking, matrix completion problem is the problem of finding a matrix of bounded rank, so that at a given entries it should be close to the given matrix. At a certain entries, like there are a number of entries, and only at those entries you require two matrices to be close.
Okay, thank you.
Excuse me, does it mean that sometimes not convex functions can give better results than the convex ones?
Yes, this is quite natural. I mean, yes, it's very often in practice, very often that you minimize something which is not convex, so for which you theoretically doesn't have any guarantees. But in practice, this works well, even more. This is the basic phenomenon behind deep learning. Maybe you have heard about deep learning when you train deep neural network. This is the basic phenomenon. That's why this deep learning became so popular nowadays. So the basic phenomenon of deep learning is general phenomenon that very often minimization of highly non-trivial, sophisticated, non-convex function. In practice, this gives very nice results. And this is the reason why deep learning became so popular. Because in the 60s, in the 70s, the neural networks had problems with financing, because everyone believed that you're stuck into local minimum, into bad local minimum in general. For some reason, this was just a stereotype that was popular. But then in the 80s, there was a reemergence of neural networks when a number of researchers independently showed that very sophisticated neural networks with many layers, they can be trained, and so the training means the minimization of loss function, right? And the loss function can be minimized. It is non-convex, but still the results are nice, and this is one of the results of modern mathematics. Nobody knows why this happens, by the way. This is a big question. Nobody knows why non-convex functions can be very often minimized very well. What is the reason?
Yes, although it's not guaranteed that they will produce global minimum.
Yes, of course, this is not no guarantees, no theoretical guarantees, but in practice, this is very often observed, and nobody knows what is the fundamental reason. Probably there are many reasons. So roughly speaking, the basic reason why we are not able to build the general theory is because, roughly speaking, there are 100 different reasons for that phenomenon. And every time we observe certain edge of that phenomenon, and we think that maybe there is one big reason for that. But probably there are no big reasons. Probably it's just we are searching for such cases, our mind trying to kind of, so many cases when we fail, we just don't notice that, and we just only remember those cases when we have success, etc., etc. So the different psychological and epistemological and many other reasons. So roughly speaking, there are 100 different reasons why we observe this phenomenon, why everyone why people believe that it's possible to minimize non-convex functions. But this is just basic phenomenon behind modern technology. So this was not believed to be true in the 70s, for example. In the 70s, nobody believed that the life is so nice that neural networks can be trained by backpropagation, for example. The backpropagation algorithm was, gradient descent algorithm was developed in the 60s, but it started heavily used only in the end of the 80s. This is because many years people didn't believe that this would be nice, but then it turns out that this algorithm solves everything. Okay, do you have any other questions?
Sorry, can you repeat what was the point of, I'm sorry if I pronounced it incorrect, Eckart-Jung-Mirsky theorem?
Eckart-Jung-Mirsky theorem, Eckart.
What was the point of this theorem? I think I missed.
This point of that theorem is that when you are given some matrix, then you can approximate that matrix with another matrix with rank not greater than k, approximated using Frobenius distance. And the best approximation is singular value decomposition of the matrix truncated at kth term. This is what Eckart-Jung-Mirsky.
Okay, thanks.
So do we use this theorem in case 2?
What?
Do we use this theorem in case 2? In the beginning, you mentioned the second case of low rank optimization problem.
You mean when in robust PCA?
Yes, yes.
That's the whole problem, that for robust PCA, this is not true. This is true for Frobenius norm, but for L2, L1 norm between matrices, this cannot be applied, unfortunately. That's the whole idea, that robust PCA problem is an NP-hard problem. So to approximate the function, the matrix in L1 norm, using some matrix with bounded rank, it cannot be done efficiently in general. So robust PCA is a hard problem. It cannot be done using singular value decomposition simply. So Eckart-Jung-Mirsky theorem cannot be applied to that case.
Excuse me, is it possible to transform the maximization problem into minimization, corresponding minimization problem? You said that the approaches basically don't work for this kind of problem. But if we take the inverse or some,
There are no easy way to turn maximization to. There is one simple standard way. F becomes minus F, and then minimization is equivalent to maximization. But then everything changes. Minus F is not convex; it's concave. So, in general, minimization are very different problems. There are one standard and simple way to connect them just by adding minus in front of the object, but this doesn't give you anything, in fact.
So NP-hard problems are the only ones that's left to research. And what about the NP-complete problems? They are fully investigated already.
Complete is a special case of NP-hard problems. It's almost the same thing. NP-complete is just NP-hard for language recognition problems. Well, this is the same thing almost. There are no difference between them, roughly speaking. NP-hard means that you can solve it using reductions, Turing reductions to NP-complete. That's the only difference. So, roughly speaking, NP-hard is a generalization of NP-complete, but almost the same thing. Okay, let's finalize because I think 1.5 hours is enough.
Okay, Rustem, thank you very much for giving the talk today. Everyone else, make sure to submit your reports, and next week we will have Alejandro Castillo as a speaker, and we will start again at 3 o'clock, the usual time. Okay. Okay, thank you everyone for participation.
Bye, everyone.
Thank
Bye.
you.